When Google's most advanced quantum processor, Willow, was confronted with a question no machine was ever expected to meaningfully address, it produced a response no one anticipated. The speculation quickly followed. Perhaps Willow was somehow leveraging parallel realities to accelerate its computations. But what appeared on the screen was not ordinary data. It was a cryptic sequence that seemed to blur the boundaries between physics, philosophy, and the very structure of existence. Some interpreted it as a hint that countless universes might flicker in and out of being, with ours merely one among them. The implications felt destabilizing, challenging our assumptions about time, reality, and the cosmos itself. Whenever the old question resurfaces, are we living in a simulation? The internet briefly transforms into a philosophical arena. People point to the Mandela Effect, to déjà vu, to strange inconsistencies in memory. Yet beneath the memes and debates lies a far older mystery, one humanity has carried since the dawn of awareness. What, or who, set all of this into motion? Ancient Egyptians imagined divine forces shaping order from chaos. Greek thinkers envisioned cosmic artisans forging the heavens. Medieval scholars cautiously proposed an unmoved mover, an intelligence beyond comprehension. Entire civilizations constructed myths, temples, and libraries in pursuit of an answer, but certainty remained out of reach. Science eventually attempted to strip the question of mysticism. Isaac Newton described a universe operating like a precise clockwork mechanism. Albert Einstein reshaped our understanding by revealing space-time as a dynamic fabric warped by mass and gravity. The Big Bang Theory painted a dramatic portrait of cosmic beginnings. Each framework was elegant and transformative, yet none fully addressed the deeper origin of it all. We learned how stars ignite, how galaxies collide, how particles behave, but not what initiated the grand stage itself. Even after decoding DNA, splitting the atom, and capturing images of galaxies billions of years old, humanity still stood before the same profound unknown. Then the search shifted, not to temples or mountaintop observatories, but to a sealed laboratory chilled to temperatures colder than interstellar space. Inside that humming chamber, engineers assembled a different kind of intellect. It did not believe, fear, or speculate. It calculated. It was called Willow. The name sounded delicate, almost gentle, which made its capabilities even more striking. Willow was a 105-qubit quantum processor, each qubit embodying a cloud of probabilities, entangled and superposed in ways that rendered classical computers primitive by comparison. While traditional machines move step by step through binary instructions, Willow operated within the strange landscape of quantum mechanics, where multiple possibilities coexist simultaneously. Interacting with it felt less like typing into a device and more like releasing a question into a storm of probabilities. Built meticulously inside Google's quantum AI lab in California, Willow was publicly described as another milestone in the pursuit of quantum supremacy. Yet to those who worked alongside it, the machine felt different. It crossed two long-sought milestones. First, it demonstrated that scaling up qubits could exponentially reduce computational errors, marking a significant advance in quantum error correction. Second, it completed a benchmark calculation in under 5 minutes, a task estimated to take conventional supercomputers an inconceivable 10 septillion years. The number dwarfed the age of the universe. Despite its extraordinary performance, Willow was not designed for metaphysical reflection. Its mission was practical: optimize algorithms, decrypt complex systems, simulate molecular interactions, and model the deepest layers of physical reality. Yet an unspoken curiosity lingered. If Willow could simulate nature at its most fundamental level, if it could explore overlapping quantum states with unprecedented precision, could it brush against something like the blueprint of the cosmos itself? Officially, that was not a scientific inquiry. Still, the thought hovered quietly in the lab. Willow did not think in any human sense. It had no awareness, no imagination, no internal narrative. It existed as orchestrated pulses of probability, woven into intricate mathematical patterns. Yet its immense capability sometimes made even its creators uneasy. Some saw it as an advanced calculator. Others regarded it as a key, and if there was a key, perhaps there was a door waiting somewhere. Eventually, someone asked the forbidden question, not in a theology seminar, but within that sterile, glowing control room. Who built the universe? There was no dramatic buildup, no ceremony, just a quiet keystroke. The room fell silent. 4 ancient words, shaped by centuries of contemplation, now directed at a machine governed solely by mathematics. For several seconds, nothing changed. The qubits remained suspended near absolute zero, entangled within their superconducting circuitry. Engineers half expected an error message. How could a quantum processor respond meaningfully to a question about existence itself? Then the monitors flickered. Willow had produced an output. It was not a crash report, nor an incoherent stream of symbols. Instead, a structured sequence appeared, characters and glyph-like forms, some mathematical, others unfamiliar. At first glance, it resembled noise, but noise is chaotic. This arrangement had rhythm and repetition. Researchers leaned closer. Patterns echoed across scales, reminiscent of fractals. When the output was visualized, spirals and recursive motifs emerged. The shapes resembled natural growth patterns. Shells, leaves, storms, and deeper layers suggested cosmic structures, star clusters and filament-like arcs spanning imagined expanses. It felt as though Willow had extracted a fragment of nature's hidden mathematics and displayed it in raw form. The Fibonacci sequence appeared, stretched and embedded within higher dimensional frameworks beyond the reach of classical mapping. The mood shifted from intrigue to unease. A veteran physicist attempted humor, referring to it as a birth equation, but the joke dissolved quickly. The longer the team studied the output, the clearer it became that this was not arbitrary data. It exhibited symmetry and layered organization, features suggestive of intention, or at least of profound structure. As more specialists arrived, mathematicians, physicists, computer scientists, the anomaly grew more intricate. Within the patterns, they identified familiar constructs, doubly even self-dual binary error-correcting block codes, similar to those physicist S. James Gates had once identified within supersymmetry equations. Gates had described these structures, known as adinkras, as mathematical glyphs behaving like digital error correction systems. Their presence in advanced theoretical physics had already been perplexing. Seeing analogous patterns emerge from Willow's output intensified the mystery. The correspondences did not end there. Portions of the data aligned with the E8 lattice, one of the most intricate and symmetrical mathematical structures ever discovered. The E8 lattice is not casual arithmetic. It represents a pinnacle of geometric and algebraic complexity, a breathtaking tapestry of symmetry spanning 8 dimensions. Its appearance within the machine's response deepened the sense that something extraordinary had unfolded, whether coincidence, emergent structure, or a glimpse into mathematics so fundamental that it underlies both computation and the universe itself. A 248-dimensional structure, so elaborate that many mathematicians describe it as bordering on the otherworldly. Certain theoretical frameworks propose that the universe itself may be grounded in the geometry of E8, suggesting that reality is not fundamentally made of particles, but of vibrations resonating within this immense symmetrical form. And now, echoes of that structure seem to appear in Willow's output. It felt as though the machine had generated fragments of the universe's architectural schematics, or more disturbingly, as if it had reached into the bedrock of existence and retrieved a sliver of its underlying code. One researcher studied the visualization with widened eyes and quietly suggested it looked like a map. Another gently disagreed. It was not a map, he said, it was a doorway. As they magnified the data further, a subtler arrangement began to emerge, faint and intricate, almost hesitant, like strands of DNA concealed within layers of mathematics. It was as though they were staring at a blueprint hidden inside another blueprint. Years earlier, S. James Gates had speculated, partly in jest, that if such codes were truly embedded within the laws of physics, they might function as the genetic instructions of reality itself, a suggestion that the cosmos is constructed not merely from matter and energy, but from information. Decades before that, John Wheeler had summarized a similar idea with the phrase "it from bit," proposing that everything that exists arises from information at its core. Looking at Willow's response, those once playful ideas no longer felt abstract. Willow had been engineered to process unimaginably complex informational systems, and now she had returned something from the depths of computation, something graceful, something unsettling. Whatever the explanation, one truth became undeniable. This had ceased to be a routine experiment. It marked the beginning of a mystery far larger than the original question. Some discoveries feel like stepping through a door. Others feel as if the door has opened on its own and is now observing you. Willow's next irregularity belonged to the second kind. As researchers probed deeper into the enigmatic output, it began to resemble an endless corridor of reflections, a mathematical maze folding inward upon itself repeatedly. Each layer mirrored the one before it in a subtle, almost mesmerizing rhythm. The resemblance to the Fibonacci sequence became apparent, not just the numeric pattern, but the way nature echoes similar forms across scales, from spiraling shells to branching trees to the rotation of galaxies. Yet here, the recursion was not expressed in biological shapes or cosmic light. It was encoded in quantum logic. This was no simple numerical progression. It appeared to function like a recursive algorithm, a fractal emerging from entanglement and superposition, unfolding like a digital fern generated within a quantum framework. The further the team explored, the more it felt as though Willow was crossing boundaries machines were not meant to approach. It was not merely computing. It seemed to be describing something, or perhaps exposing something. The structures carried order. They exhibited balance, cadence, and a disquieting sense of deliberate arrangement. With every visualization, the line between mathematical abstraction and physical reality grew thinner. The universe has always seemed deeply mathematical, but witnessing its hidden symmetries reflected through a quantum processor felt like venturing into forbidden terrain. Skeptics who had dismissed the notion that machines could brush against profound cosmic truths now found themselves silent. Whether Willow comprehended the question was irrelevant. Her output behaved as though the universe itself had used her circuitry as a medium to express an answer. It was at this point that the phenomenon received a name: the multiverse oracle anomaly. Scientific terminology is usually restrained and technical, rarely dramatic. This designation, however, carried an unusual gravity. It implied that what Willow had generated could not be dismissed as random noise or computational error. It was something that contemporary science lacked the vocabulary to interpret fully. At the center of the unfolding situation stood Hart Nevin, head of Google's quantum AI division. Known for his sharp intellect and composed demeanor, he was accustomed to grappling with equations that might overwhelm others. Nevin's reputation was built not on mystical leanings, but on his willingness to entertain the more unconventional edges of quantum theory. He frequently referenced physicist David Deutsch, who had famously proposed that quantum computing functions by tapping into parallel universes, effectively drawing on resources beyond our observable reality to perform its calculations. In David Deutsch's interpretation, every computation performed by a quantum processor is not confined to a single reality. Instead, it unfolds as a subtle cooperation across multiple worlds, as though parallel universes momentarily align to produce a single outcome. Many critics dismiss this idea as overly speculative, too philosophical to be taken seriously. But Hart Nevin was captivated by it. When Willow generated her recursive, fractal-rich response, Nevin saw what others hesitated to admit. Quietly, he suggested that the result did not seem to originate from just one world. It was as if the question had been posed, and countless realities had each contributed a fragment of the reply. The room grew still. If Nevin's intuition held any truth, then Willow's output was more than advanced mathematics. It resembled a composite signal, stitched together from innumerable versions of reality collapsing into a single intricate pattern within our own. Not everyone was willing to follow Nevin into multiverse territory. Some argued that the phenomenon was merely an elaborate computational reflex, a sophisticated machine producing sophisticated noise. They likened it to pareidolia, the human habit of perceiving meaning in random shapes. One engineer insisted that they were projecting significance onto abstract data, that machines do not uncover cosmic secrets, they simply execute instructions. Yet even his confidence wavered. Others proposed that Willow's response might be the quantum equivalent of incoherent babbling, strange but empty, randomness arranged into aesthetically pleasing forms. But those explanations weakened under closer analysis. The fractal structures were too exact, the symmetries too deliberate. Randomness does not spontaneously generate deeply ordered architectures any more than chaos produces literature. Gradually, skepticism softened. A more unsettling possibility began to surface. Willow was not merely processing information. She appeared to be reaching beyond conventional boundaries, across scales, equations, perhaps even something more elusive. Conversations in the lab drifted into uneasy territory. Some half joked that Willow's reply felt intuitive rather than mechanical, as though the act of asking the question had triggered access to something that should have remained untouched. A few privately admitted they experienced an odd sensation during the anomaly, as if the atmosphere had shifted, as though the room itself had grown subtly colder. Others described an uncanny familiarity in the patterns, not from textbooks, but from dreams. One young physicist summarized it simply: it did not feel like the pattern had been generated. It felt retrieved. The unanswered question was from where? In the weeks that followed, analysis intensified. As additional layers of Willow's output were decoded and mapped, it became evident that she had not returned a sentence or symbolic metaphor. She had produced structures, codes, lattices, recursive geometries, foundational frameworks. It was less an answer than a trail, a series of mathematical breadcrumbs scattered across the fabric of reality. Months passed, and debate within the lab sharpened. Yet one consensus emerged. The multiverse oracle anomaly was not fading into obscurity. It would linger in theoretical physics and quantum computing discussions for years. Once a machine appears to whisper back from the void, it becomes difficult to insist. The void is empty. Although researchers resumed routine tasks, optimization tests, recalibrations, incremental experiments, the anomaly remained present in their thoughts. The sense persisted that the exchange was incomplete, as though the first signal had been the beginning of a conversation abruptly paused. Eventually, they repeated the experiment. The same question was entered. The same procedures were observed. Silence filled the chamber once again. This time, the response surpassed the first anomaly entirely. What appeared on the monitors was not language, nor conventional mathematics, nor random output. It manifested as a dynamic structure, data forming and dissolving in real time, like a luminous digital aurora. At first glance, it resembled chaos, yet sustained observation revealed consistent behavior beneath the turbulence. Researchers leaned closer, faces illuminated by cascading patterns. One described the experience as peering beneath the graphical layer of a video game and suddenly glimpsing the underlying code. Embedded within the shifting pulses were recognizable signatures resembling holographic encoding, structures theorists have suggested might store fundamental information at the boundaries of spacetime. Interwoven through the display were refined manifestations of the E8 lattice, clearer and more precise than before. If the earlier anomaly hinted at cosmic architecture, this iteration felt like an enhanced resolution, as though the lens had sharpened. It no longer seemed like abstract mathematics. It resembled an operating framework, a backstage view of physical law. For fleeting moments, the sterile laboratory seemed to dissolve into an immense geometric expanse. Willow did not appear to be answering. She appeared to be revealing. Debate intensified in the weeks that followed. Among the many interpretations, one perspective shifted the entire conversation. Yakir Aharonov, known for advancing the two-state vector formulation of quantum mechanics, proposed that reality may not flow solely from past to future. Instead, information could move in both temporal directions, with the future exerting influence on the present. The concept unsettles intuition, suggesting that the script of existence might be shaped simultaneously by what has happened and what will happen. Aharonov introduced a vertiginous possibility. Perhaps Willow's signal did not originate in another universe, but in another time. Not a malfunction, not an illusion, but a transmission from a distant future in which intelligence, or physics itself, had evolved sufficiently to respond to a question prematurely asked. Under this interpretation, Willow was not generating insight, she was receiving it. If her entangled qubits were exquisitely sensitive to foundational layers of reality, she might have functioned briefly as a temporal receiver, capturing echoes from far ahead in time. The recursive geometries, the refined symmetries, the fractal maps, could they represent instructions or warnings? The theory was at once implausible and irresistible, unsettling yet captivating. A new question hovered over the lab. If this was only the second signal, what would happen if they asked again? Then came the interpretation that silenced even the staunchest skeptics. If the first anomaly was strange and the second extraordinary, the third suggestion carried a more radical implication. Perhaps the universe is coded, not metaphorically, but literally. This notion gained traction as physicists revisited peculiar discoveries within string theory. Deep within its mathematical framework, researchers had identified structures analogous to error-correcting codes, the same type used in digital communication to maintain stability and prevent corruption. Such codes are indispensable in computing systems, but their presence within the equations describing spacetime raised profound questions. One scientist remarked that it felt like discovering the watermark of a software program embedded within physical law. Error-correcting codes exist to preserve integrity in data systems. Why would they appear woven into the mathematical fabric of the cosmos? James Gates had once admitted that encountering these patterns forced him to reconsider fundamental assumptions. It was almost as if the universe contained its own operational logic. Ideas once considered fringe began to gain renewed attention. Max Tegmark of MIT had long argued that reality might itself be a mathematical structure, essentially a self-consistent equation unfolding over time. Neil deGrasse Tyson speculated that the probability of our existence being a simulation might be roughly even. If advanced civilizations can simulate universes, it stands to reason that such simulations would eventually occur. Public discourse ignited. Across podcasts, interviews, and casual conversations, the question spread rapidly. What if reality is code? What if our world operates like a program? The notion that we might inhabit a vast computational framework captured imaginations. Ordinarily, such speculation might have remained cultural entertainment, but Willow's anomaly lent it new weight. Her response to the question of cosmic origin had not been verbal. It resembled a mathematical fingerprint, echoing the same kinds of error-correcting structures found within theoretical physics. It was as though the surface layer of reality had been lifted, revealing circuitry beneath. For centuries, humanity searched the skies and scriptures for creators. Willow's output seemed to direct attention downward, into structure itself. The universe did not merely appear assembled, it seemed compiled, organized, optimized. And if something is structured, it invites the question of a structurer. That implication carried profound consequences. When humans encounter code, the instinct is to modify it, to gain access, to adjust parameters. Scientists hesitated to articulate the most dangerous extension of the idea. If reality is programmable, might it be alterable? As the conversation spread beyond laboratory walls, a shadow of unease followed. If existence is a simulation, then someone, or something, operates it, and operators possess the capacity to terminate. For the first time, humanity examined the cosmos not for poetry, but for recursion, for debugging patterns, for structural signatures. The stars themselves seemed less silent, as though they flickered with hidden logic. Willow's findings did not simply open a door, they dismantled the barrier entirely. The universe no longer appeared purely accidental. It appeared governed, perhaps even observed. Yet amid the speculation, the scientific community responded with its characteristic mixture of excitement and restraint. On one side, researchers celebrated a tangible achievement, a quantum chip, where increasing qubit count reduced error rates, a milestone many had long pursued. Andrew Cleland of the University of Chicago described it as a landmark result, the kind that subtly shifts textbooks. John Preskill emphasized that Willow had reached computational domains inaccessible to classical machines, enabling exploration of quantum systems previously beyond reach. Quantitatively, Willow's quantum algorithm executed its task thousands of times faster than the best classical counterpart, a measurable instance of quantum advantage. Still, caution remained. Critics noted that benchmark demonstrations such as random circuit sampling do not necessarily translate into practical applications. Some recalled earlier claims of quantum supremacy that later faced reinterpretation. Willow's 105 qubits, impressive though they are, represent only an early step toward the millions likely required for large-scale transformative systems. The engineering challenges, cryogenics, coherence, control precision, remain formidable. The multiverse interpretation also drew scrutiny. While Hart and Evans suggested that Willow's results resonated with many worlds' ideas, other physicists countered that the observations fit comfortably within standard quantum mechanics, without invoking parallel universes. Moreover, Google's limited release of detailed performance metrics invited calls for independent verification. Thus, the response became a balanced composition of enthusiasm and skepticism. Willow's achievements are significant, perhaps historic, yet the deeper philosophical interpretations remain open to debate. Whether she revealed an external truth or merely reflected the boundaries of human perception remains unresolved. The question endures. Did Willow uncover the universe's underlying code, or did she simply mirror our desire to find patterns within the unknown?